All right, we'll let the few people filter back in. I'll give them a second. I knew you'd be the first one to come back. You just love to swear, don't you? I mean, I swear in my daily life all the time. So it's okay. I don't think that that's a problem. I don't believe in censorship. Okay. So today we're learning about the inverse to this function right here. X times e to the x. So we've all got back. Yes, floor gang. We're all on the floor. So welcome to It's Time Again. Try to keep the swear. I mean, try to be reasonable. Try to keep it to a minimum. Try to keep the swearing to a minimum. So let's call this f of x instead, because we're going to be interested in the inverse function. And I think function notation warrants itself to talking about inverses a little more, because you won't be convinced to try and do like reciprocals when I do the -1 thing. So why does that look much straighter in person than it does on the screen? Whatever. If we take, say, the derivative of this, we just have to do the power rule, the product rule, right? So the derivative of the first one is 1 times the second one, so e to the x. And then we keep the first one and take the derivative of the second. So we get x times e to the x, which is the same thing as that. Right? So that's the derivative of that function. The integral is sort of the same. You can actually define it based on this. So the nth derivative, and this goes for any index n. This could be fractional, complex, imaginary, negative. It's just e to the x times x plus n. So if you want to do an integral, this will just be minus n, right? It's really quite nice. Where is the Lambert W function bijective? The Lambert W function is bijective nowhere, right? Wait, what are you telling me to prove? You're telling me to prove this fact? It's really quite easy to see. You just take any number of derivatives or any number of integrals, and you'll keep seeing the number of derivatives that you see appear here. And then you just sort of generalize it from there. Maybe another time. It just is the best way to transition between them. I guess you mean you want me to use like the definition of the fractional derivative. I'm not about to do that right now. Point is, what we want to do is we want to try and think about the inverse of this function. So what we have to do is define something that is, by definition, the inverse of it. So we'll say that w of f of x, which will be w of x times e to the x, is equal to x. So this function w is going to be our inverse function, right? This is going to be the thing that undoes f of x. And so let's see what we can do. Because we know that w of f of x is equal to x, and now I'm going to say w of y. I'm going to replace f of x with y. That means we can just replace the x's in the original equation with w of y, right? Well, I appreciate the comparison, but sort of on the same vein of what Luis said before, I am trying to do my own thing, but I appreciate the comparison. He's a very good YouTuber. So we're going to replace f of x with y, right? And we have y is equal to, and what's x? X is w of y, right? We're replacing the input with the inverse function, because that's what would allow us, you can see that is what would be allowed. So now we can sort of find some things out about the Lambert W function. We can divide by it onto one side, and we get that e to the w of y is equal to y over w of y. So this is going to be an important fact. This is going to be an important fact. So as you can see, if we just reciprocated this side by making this negative w of y, this would just flip this fraction. So let's see how this can be useful in other things, because it's good for finding the inverses of other functions. let's see. So what do we want to look at? What should we look at first? I guess this gives us one more identity we can do. So if we take the logarithm of both sides, we actually find out that w of y is equal to log y minus log w of y. Right? Because we're just taking the logarithm of both sides, the log and the e cancel, and we just get w of y, et cetera, et cetera. From here, we can actually figure out, we can actually use this to figure out the derivative of the w function, because now we have it in terms of other things. So let's take the derivative. So we get w prime of y, and we're doing this with respect to y, equals 1 over y minus, this is the logarithmic derivative, so we get w prime over w. And so we want to solve for w prime now, so we add that over and factor it out, so we get w prime is equal to 1 plus 1 over w of y, and that equals 1 over y. So we can multiply that over, and we end up with, what do we get? We divide that over, and we get that w prime is equal to 1 over y times, so this is going to be w plus 1 over w. So we're going to get w of y over w of y plus 1. And I think if you go onto Wikipedia and you look up the Lambert W function, that is the derivative that you will see. Lambert was a German mathematician in the 1700s. We can also figure this out by using the general inverse derivative of an inverse function, because we know what the derivative of this function is. It's this right here. So all you have to do is plug in the inverse function w into 1 over the reciprocal of the derivative of the original function. So if we just replace these x's with w of x, we'll be able to get this result here. Or replace the x's with w of y, whichever variable you want. We would get this result down here. So they're the same thing, and you will get that answer. So we know the derivative of the w function now. So that's interesting. That's useful. Shall we consider the inverses of other functions? So let's see. What we can do is, what I think to be an interesting question is tetration and power towers. So if we take a look at the function, that blue light is from my microphone, by the way. I don't know if you can see that blue light. So we're going to take a look at, say, g of x equals x to the x. And we'll say this is also equal to z. Okay, so z is a function of x, and it's x to the power of x. And I want to find the inverse of this function, right? I want to find the inverse of it. So this is going to be something that's usually called the super square root, because say we're looking for a number that requires raising one power to the other. So what's the super? It's usually notated like this. The super square root of x is going to be the inverse of this function, just like the square root of x is the inverse of x squared. Because what's this in tetration notation? It's the second tetration of x. It's like a power, but to the top left instead. And so that's usually the notation. And this means repeated exponentiation. So for example, the super square root of 4 is 2, because 2 squared is 2 to the power of 2 is 4. And if you asked for the super square root of 2, it's some weird number like 1.59 or something like that. Yes, the Wikipedia articles are interesting. Will you also be looking at the superlog? I might. I'm not as well versed on that, but sure. What is polylog? That's sort of a completely different thing. That's like a combination of a power series and a Dirichlet series in 2 different variables. Some of them simplify and evaluate to very nice and simple elementary functions, but not all of them, to the best of my understanding. Papa Flammy mentions them in his thesis stream. So I want to find the inverse of this function. So what I'm going to do is I'm going to flip the variables. So we want g inverse of z, which is going to be equal to x, right? And so I want this to be equal to, I want this to be x equals z to the z, and I will sort of, that's not what I wanted. That's not what I meant. I want to find G inverse, sorry, which is a function of Z, which means I need to solve for Z in this equation, right? And the Lambert W function is exactly, yes, thank you, Tank. It's almost like that's where I'm going with this. So what I'm going to be solving for when I solve for Z is the super square root function. And you actually can't really put this into a nice, neat, closed form without using the Lambert W function. So let's take a look at that. So I'm going to take the natural logarithm of both sides. And now, what do I want? I want to be able to have something times e to the power of that same thing so that I can apply w to both sides and just get that thing back. And that's almost what we have here, except we have it with z and a logarithm. So what I'm going to do is I'm going to rewrite z as e to the power of the natural logarithm of z. So this becomes ln of z times e to the power of ln of z, right? Because e and ln cancel and we just get z back. Right? And so now I have this equals this, and I'm going to do Lambert W to both sides, and we get W of natural logarithm of X is equal to just ln of Z. Right? So just ln of Z. And raise e to both sides, right? And this just gives us z back, which solves for our inverse function. So in terms of this inverse of x times e to the x, we now have the super square root function. But because of that identity we were able to find before based on this exponential thing, this is going to be equal to ln of x divided by w of ln of x. Because remember, we were able to show that e to the w of x was equal to x divided by w of x. So we're just replacing x in this case. Whoops. We're just replacing x in this case with the natural logarithm of x. So if you wanted to plot this somehow in Desmos, you would need one of the integral representations that you can find that I will be proving eventually on this channel. But this is a way to express the super square root of a number. And funnily enough, the only other tetration problem that you can use the Lambert W function to solve is the exact opposite extreme, because it doesn't really get to be interesting tetration until you get to two of them, right? The first tetration is just the number x. But the Lambert W function is only good for the second and the infinitieth tetration of x. It's only good for those two things. For the third tetration, 1, 2, 3, you need to define other inverse functions to other functions that are literally more like stacked versions of this function right here, which I will also be getting into. Why is tetration so rare? Because it's so obscure. It's not that useful for physical applications, it seems. Like it either grows incredibly quickly or gets incredibly tiny so quickly that it's like it doesn't have elementary sides to it. So it just doesn't lend itself to being particularly useful. But let's quickly analyze the other function that this is good for solving. So let's keep this on the back burner, right? The inverse, the super square root of a number, z is x to the x is ln of x over w of ln of x, where w is the inverse of this function here, the Lambert W function. So we're going to take a look at one more function, which is actually the infinite tetration, right? Have a lovely evening, Mr. Edward from Poland. I believe it was you who was from Poland. Have a lovely night. Please get some rest. So now we're going to explore the infinity tetration, right? It goes forever and ever. This can also be expressed as such, right? You just replace the tetration number with the symbol for infinity. But of course, if we cover up that bottom x, you'll notice there's another infinite tower of x's, which is of course equal to z. So I can write this as x to the power of z, right? And now we can sort of solve for z, or flipping everything to get the inverse thing in a very nice way using, again, the w function. So I'm going to let this be x, and then we're going to have z is to the power of x. So now I can solve for z and get the oh no, I'm sorry. Now I can solve for z, but notice if I solve for z, I get z is equal to x to the power of 1 over x, which is an elementary function, right? This is an elementary function, which means the inverse of this function is equal to the infinite power tower of x, which is really weird, which means we will be able to solve for this function, the inverse of this function, by simply switching the roles of x and z. So we solve this equation here, which is pretty neat. It's pretty neat that that sort of just appears out of nowhere. So we're going to take the logarithm of both sides. So we get ln of x is equal to 1 over z times ln of z, right? Cool with that? And we're going to do the same trick that we did before, but first we're going to multiply both sides by -1. Because what happens when I multiply both sides by -1? I can take that -1 into here as a power, right? Like that. So it's the natural logarithm of z to the -1, right? Over z times the natural logarithm of 1 over z. Of course, I can write 1 over z as e to the power of the natural logarithm of 1 over z. So we get ln of 1 over z times e to the ln of 1 over z. Is that visible to everybody? I think so. And so then we're going to apply w to both sides again. And so we get w of negative ln of z is equal to ln of 1 over z. So we can multiply both sides, or we could do e to the thing again. So we get 1 over z from here is equal to e to the w of negative ln z, which is, of course, equal to negative ln z over w of negative ln z. And then we want to solve for, and these should all be x's. My mistake, sorry. This should be an x, this should be an x, this should be an x, and this should be an x. My bad. Sorry. We're solving for z. So now we just reciprocate both sides, and we get that z is equal to w of negative ln x divided by negative ln x. So notice the inverse of this function is this funky looking thing. And the inverse of this function is this thing. So I'm sorry, that's not very neat. So this is w of negative ln over ln. This is ln over w of ln. So if you plug in 1 over x into here and then reciprocate that, you end up with that. Isn't that kind of weird? Very strange. Very odd that they're tied together like that. But as soon as you try to ask what the inverse of, say, this is, just 3, you're completely lost. You're completely lost with trying to use the Lambert W function. Yes, there is a part of the domain that does have 2 answers, because this function right here looks sort of like this. So this is the x-axis. This is the y-axis. This function right here looks sort of like this. So when you invert it, you end up with, because it fails the horizontal line test for everything. So this is negative 1 over e in the y direction. So everything and this is -1 right there. So this is everything that's greater than everything that's less than 0 and greater than -1 over e fails the horizontal line test. So when you invert it, everything from -1 over e to 0 is not well defined. But yeah, I don't know that I really want to talk about hypergeometric functions. They're just kind of crazy. Hello, Cyrus. So yeah, but unfortunately, this function is just simply not powerful to find an inverse to something like this. It's not powerful enough. But for some reason, it's powerful enough to solve the 2 tower case and the infinite tower case. But anything in between, it's not good for. You actually need to explore functions like this. to be able to solve this problem. And then I have, a hunch that you need sort of a similar quadruple version to solve the 4 version. And then I really, really wonder, would it then make sense to you actually to completely cut off for a second, the Joker, you understand that by defining the iterative process over powers of I. What's funny is that if you do tetrating over I to the I, you get a weird number. It's funny. I'll take a look at that right now. But I have a feeling that you need like this repeated version of this function to solve the n tower. And then I wonder if you take this to infinity, could you then rewrite this in a way that it still goes back and helps you solve the infinite case, even though we were already able to do that with the W function? I wonder. Would we be able to do that? I'm not sure. I'd have to think about it. So the infinite tetration of I is like an iterative thing. So hang on one second. Whoa, falling over. Hang on one second. So yeah, let's actually let's just take a look at what was I just thinking about. It's not commutative, so it's pretty hard. Yeah. Power towers are weird. I completely agree. They're very, very strange. They are straddling the line between elementary function and non-elementary, and it's hard to understand them in a certain sense. And one of my generalization videos has to do with these, my generalization bombs. So next one I do is going to be on this stuff, and that's to you. That's to you, Jens. I'm coming after you. So let's. What did I want to consider? I wanted, so these are pretty much intractable. But you can answer relatively interesting questions with the W function. And there's, oh, yes. So there's a famous constant associated with them. We want to know when f of x is equal to 1. So we know that we can just replace x with w of the input. So we know that this has to be w of 1 times e to the w of 1. And now w is a multi-valued function when considered in the complex plane, and so it has branches. So I'm talking about the principal branch right now. And w of 1 is special in this way because this is just 1 over here, so we don't really need to include it in this. And what do we end up with? We end up that w of 1 is equal to e to the negative w of 1, which implies that negative w of 1 is equal to the logarithm of w of 1, which is neat. It's kind of sad. That's funny. Let's see if I can fix that. You can hear me now, right? It's kind of sad. That was funny. I unplugged the mic. Let's see if it works if I plug it back in. Hello? Hello? Can you hear me? Are you able to hear me? What about, I know there's a bit of a delay. Can you hear this mic now? Cool. All right. How long was that? Like a minute? That's funny. Okay, so yeah, I think it's more revealing to sort of iterate the process. I might have accidentally just turned it off. So we want to first consider the first tetration of something as just that thing on its own. So this is just I. And the second tetration is that thing to the power of itself, which if this is I, we can just raise this to the I power, and we end up with e to the negative pi squared, pi over 2, sorry. So e to the negative pi over 2, and it's actually a real number. Right? So that's quite a surprising fact. So yeah, now we're gonna sort of layer it. So what we want to do is we want to first consider what would I to a general complex number be? It actually seems like it's more difficult to understand, but it's actually going to be very enlightening, because what we can do is rewrite this as e to the I give me 1 second, e to the I pi over 2 times a plus bi, right? Because I is e to the I pi over 2, right, from Euler's formula. We just distribute this in. And yes, the first tetration of I is very funny. And then we just distribute this in, and we get e to the negative b pi over 2, right? Because I times I is -1, plus I, plus, and then I'll just bring this into, well, times e to the I pi over 2 times a, right? And now we can use Euler's formula to transform this, and we get e to the negative b times pi over 2 times the cosine of pi over 2 times a plus I times the sine of pi over 2 times a. All right? Makes sense? Can everybody see that? All I did was Euler's formula, right? I just replaced this with this because that's Euler's formula. Simply distributing the things in, we get the real and imaginary parts of this new number are e to the negative pi over 2 times b, all times the cosine of pi over 2 times a, plus I times e to the negative pi over 2 times b times the sine of pi over 2 times a. So this is the real part of not the module. Do you mean the modulus? Is that what you meant, the modulus? This is the real part of this expression, and this is the imaginary part of this expression. And all you have to do is determine what a and b are, and you can just plug them into this equation. So this is sort of like saying I is the first term, and then we're plugging in 0 for a and 1 for b, so that we're raising I to the power of I. And then we evaluate this, and we will get this number right here. And then taking this, so we're setting a, then we're setting a equal to this number and b equal to 0, and then we're letting that evaluate and see what we get, right? So we're just taking this number and plugging it into here. And essentially what this does is it sort of spirals inward on the complex plane to a number that's like, I think, about 0.4 times 0.5 I, but it's, you know, irrational. What's kind of funny, is that what if we infinitely tetrate this? So Oh, that might be the way to do that. Interesting. So I just had a thought, but I like complex numbers. Well, the double helix, I promise, I'm going to be doing a complex analysis series because I decided that's something I want to do. So I promise we'll see it happen. It's a beautiful, beautiful subject. Like, it's truly one of the gems. So yeah, shall we? In fact, the 10 or 11 of you that are in the room right now, I'm gonna. How does analytic continuation? Is there a formula for it? Analytic continuation is a name for a method of expanding the domain of definition of functions. It is not a set in stone thing. It's a part of complex analysis because things become much more nice abbreviation, Major. Become much more open and understandable when you expand from just the real one-dimensional line to what's the word? The two-dimensional plane, right? So what I want to do now is actually sort of probably pull something out of left field from the perspective of the double helix, and I'm going to prove to you a really amazing result, something that I think is just beautiful. And I'm going to skip over like one of the rigorous parts of it because I think the level of symbol heaviness that it is for the point of being rigorous, but not really gaining much more understanding is not worth it. So if you recall, we said that the Hilbert W function evaluated at 1 on the principal branch is equal to this omega constant, such that W of 1 times e to the W of 1 is equal to 1. Right? That was the thing that we said. Yes, I understand that they're not associative. It's just funny to do it because you end up with a not so weird number. Yes, I understand that it's not commutative. Tetrating is very, very weird. I'm pretty sure you lose something every single time you do another operation, but maybe I'm mistaking that for something else. I'm going to prove to you. So this is about, hang on, this is about 0.567, right? That's approximately that number. It appears that there's another delay with the sound in the video. I hope that's not that annoying. I'm going to prove that this is true. So, isn't that something to behold? And if you plug this into there, you get about 0.638, as far as I'm aware. Yeah, they are very similar, which is kind of funny. You know what's weird? I'm pretty sure that pi divided by 2e is really, really close to the Euler-Mascheroni constant. I'm pretty sure pi divided by 2e is something like 0.5778 or something like that. But it's very close to Euler-Mascheroni. So this is just about the Euler-Mascheroni constant, which is kind of funny. Probably just a mathematical coincidence, though. I mean, I'm sure maybe there's some estimation where this is useful. Ooh, maybe this comes out of like something to do with like the Stirling approximation for the gamma function. I have no idea. Maybe, not sure. But yeah, this is a truly beautiful integral right here that I want to. Yes, you know, Shardmaster, that's what I was thinking of. You're absolutely right. Oh, what you end up with higher operations is branching points about what inverses you could have, because as soon as you get to exponentiation, you can get the logarithm or the root, and here you can also get super root or the complex or the super logarithm, and I think there's other ways you can break it up too. So we're going to prove this integral. It's absolutely bonkers. I mean, this function is ridiculous, and this result is ridiculous based on what we know about the Lambert W function, but it's in fact true. And unfortunately for Mr. Helix, in this case, I do have to use some complex analysis for I know not how to do it otherwise. So, and we actually need the Lambert W function, or else this wouldn't appear, right? We need to be able to solve this using the Lambert W function. So let's take a look at this. So there's this thing in complex analysis, right? We're doing an integral on the real number line from negative infinity to positive infinity. So the entire real number line. Inverse is because the power is the multiplicative inverse. Of course, we're just using residue theorem, Joshua. Come on now. Of course we are. It's one of the most beautiful facts. So, yeah, but not everybody knows complex analysis. So this seems like a complete magical mystery on the face of it, because what you're able to do in complex analysis is observe that this function here might have solutions that are not on the real number line, things where it equals 0, values of t that are complex numbers that aren't on the real number line, and so that make it 0. And in fact, you can sort of cheat at this a little bit by doing what's called a contour integral. So we're going to do a contour integral where we want to somehow do an integral along the whole real number line. So we're going to go from negative r to r, and we're going to integrate over that. But what we're going to do is we're going to recognize that there's solutions on the complex plane to this function under here that make it 0, and we're going to integrate around them as well and do a whole semicircle of integration where r is going to get bigger and bigger, and this is just a semicircle, and it's going to expand out. And the rigorous step that I'm going to jump over and not really go into detail is considering how all of these solutions of this function, because of the different branches of the W function, sort of make this a much more detail-oriented problem to solve. And I'm just going to take for granted that this semicircle, as it goes out, is the integral over that is going to approach 0, and the sum of all the residues, which I will explain in more detail, of all of the zeros under that semicircle, they all cancel each other out, except for the one that is the principal solution that we'll be using to prove this. So that's the rigorous step that I'm jumping over. Yes, I'm doing a semicircle contour. Very poorly drawn one. So essentially, what the thing about complex analysis is you can take an integral around stuff, and then all you need to do is take the point that this is, so z0 for some z, and sort of divide the function, multiply the function by the solution at this point. So say f of x, or f of z in this case, is, say we have f of z is equal to some other function, g of z, divided by z minus z0, where z0 is some solution to the function, right? So say this is z0 right here. If we plug it in, we're going to be dividing by 0, and that's a problem. So there is this thing in complex analysis called the residue of a function. And essentially what it is we simply multiply this problem spot over to the other side, so we're no longer dividing by 0. And now we're left with whatever function f was, but without that problem point. And then we simply let z approach z0, because this is going to blow up. Well, maybe. This could have been 0 at that point, but it's going to be undefined at that point. But then we're going to be multiplying by 0, so everything's going to cancel out nicely anyway. Now, the integral over this closed loop containing these points is just the sum over all of the solutions in that set. So, up to some capital N, however many zeros there are. If there are countably many, I believe this works. I only know the proof, or understood the proof for finitely many. Is everything's still audible, right? So as it turns out, the integral under this contour is 2 times pi times I times the sum of all these things, and this is the limit as z approaches zn. And we're going to find out that all of these solutions, other than the one at the principal branch that gives us this right here, they all cancel out in this example, which is why you just end up with this nice and simple answer in the end. And so I'm going to take that fact for granted, and it will be clear what we're doing. So first, I need to figure out where this expression is equal to 0, where the function on the bottom is equal to 0. So we have e to the t. I suppose I'll do e to the z. So t is the dummy variable for integration, but these are complex numbers. So e to the z minus z squared plus pi squared equals 0. Right? All we're going to do is we're going to solve for z, but we need the Lambert W function for this. So we subtract pi squared over, and we take the square root of both sides. So we get e to the z minus z is equal to the square root of negative pi squared. So we're going to get plus or minus I times pi, right? And we're going to end up only integrating in the top half of the plane, so we don't actually need the lower one. We're just going to stick with the positive example for now, because it's going to cancel anyway when we use the Lambert W function to solve for z. So what we're going to do is we're going to raise e to both sides of the equation, right? And now this part right here can be rewritten as e to the negative z times e to the z. And this is negative 1, right? Because that's from Euler's formula. But I want to be able to do the Lambert W function of both sides, but I need the thing that's being multiplied and the thing in the power to be the same. So what I actually need to do is divide these two things to the other side of the equation, right? Because then I'll get 1 on this side, because I'm just dividing both sides by that thing. So I get 1 on the left, and now I have negative e to the z times e to the negative e to the z, because I've reciprocated those. And you'll notice I have that there and that there. The same thing that's being multiplied over here and the same thing that's being multiplied up there. And so I can use the W function. That's where omega comes in, because this is 1. So I apply the W function to both sides. And I get that W of 1 is equal to negative e to the z. Multiply the negative 1 over and take the logarithm of both sides. And I get that the natural logarithm of negative W of 1 is equal to z. I hope everyone's following that argument so far. I did not try the integral you showed me. In fact, I don't actually remember what it is. So if you could repeat it to me, I would totally try it. And so the logarithm has the property that if there's a product underneath a log, you can break it up as the sum of those logs. So we have log of negative 1 plus ln of W of 1 equals z. We all know what the natural logarithm of negative 1 is. It's I pi, because e to the I pi is negative 1. So the logarithm of negative 1 is I times pi. And what were we able to prove about this, right? We can divide e to the W of 1 over, take the logarithm of both sides, and we get that the log of W of 1 is negative W of 1. So this is negative W of 1, and this is I times pi, which means on the principal branch, z, the solution to this equation here, is really just negative W of 1, or negative omega, plus I times pi. So that's really quite, what's with the plus 2k pi I? Are you talking about like with the argument of the thing when it, depending on how many times you spun around? I'm not really doing that because I'm doing principal branch, so the argument is part of the principal branch from negative pi to pi. And so we're only considering this solution right now. Now, I want to know what this divided by this is in the limit as it approaches this new number that we've solved, right? We set the denominator equal to 0, and we solve for when it equals 0. So we've been able to show that z0 equals negative W of 1, which is again omega, plus I times pi, is a solution to this equation in the denominator, right? And so now I want to be able to calculate the residue of this equation, so I can figure out the sum of the total residues under the integral. So what I need to do is multiply 2 pi I. And the reason I'm only considering this one is because, like I said, it's true that all of the other solutions, when you add up the residues, they cancel. And so they don't matter. And that's just too much rigor at this point in the evening for me to care about doing that right now. So just understand that this is the only residue that's going to end up mattering. And that's why this fact ends up being true. Okay? So we multiply 2 pi I, or no, we're not going to multiply by 2 pi I yet. In fact, it's going to be a magical moment when we have to. So we're going to take the limit as z approaches this number, z0, of, we're going to, remember, we're multiplying this function by the problem point, which is z minus z0, to cancel the solution in this denominator so that we can allow z to go to z0 and we have a defined amount. And we're dividing this by the function. So e to the z minus z squared plus pi squared. And of course, if we plug in z0, we're going to get 0 over 0. So we need to use L'Hopital's rule, which involves taking the derivative of the top and dividing it by the derivative of the bottom and letting z go to the number. The derivative of the top is quite easy because the derivative of z is just 1. z0 is a constant. So we're going to get the limit as z approaches z0 of, and the new numerator is 1. And the derivative of the bottom is just, we got to use the chain rule. The derivative of pi squared is 0 because that's a constant. So we bring the 2 down as a power. So we get 2 times the inside. So e to the z minus z times the derivative of the inside, which is e to the z minus 1. Cool so far? I hope we're cool so far. The 10 of you that are still here are absolute champions. So we're going to let z approach z0 now, but this is z0, right? So we just have to ask ourselves, what's going to happen when we plug this into here? Well, we already know that e to the I pi is going to be -1, and e to the negative w of 1 is just w of 1, right? Because if we divide e to the w of 1 over, we just get w of 1. This one's actually on Wikipedia, and I just wanted to know the proof of why this was true. This is on the Wikipedia page for the omega constant, which is this, and the page for the Lambert W function. So we're just going to plug this into here. We already know that e to the negative w of 1 is just w of 1. You can see that by dividing this to the other side of the equation. So we're going to get 1 over 2 times e to the negative w of 1 is w of 1. And e to the I pi is -1. So that's going to get multiplied by -1. And we're just plugging this in for z now. So we get w of 1, because we're doing minus w of 1. So that's plus, and then minus I pi. And then we have to fill in this one. And so we're plugging this in again for z here. And we get e to the I pi is -1, and e to the negative w of 1 is w of 1. So we again get negative w of 1 minus 1, right? Minus 1, right. Isn't pi a variable that goes to 3 as it approaches e? That's lovely. That's a beautiful meme. And you'll notice we get some absolutely stunning cancellations in here. So let's see. Let's see if I can aim this down correctly. Because look, we have negative w of 1 plus w of 1. Those cancel. We have a -1 here, and all of these get multiplied by -1, and we cancel that. And we're left with 1 over 2 pi I times 1 plus w of 1. But what do we have to do when we do residues, right? The residue, or the integral over the contour, is 2 pi I times the sum of the residues, or all of them that matter. And so when we multiply by 2 pi I, we actually cancel with the 2 pi I in the denominator, which is absolutely bloody brilliant. Because then we're left with 1 over 1 plus w of 1. And w of 1 is the omega constant. So that, in a sort of rough sense, proves that this integral must be true. I hope that that is a satisfying demonstration of that fact, because dealing with all of the other things underneath the contour that actually do have to cancel out if you want this to be a rigorous argument, it's very, very boring and very, very tedious and very, very symbol heavy. So I hope that that is a satisfying result. It is, if you understand the residue theorem. And so just to say to Mr. Double Helix, when I finally do an explanation of complex variables, I will have you understanding the residue theorem and how you can solve some amazing, amazing integrals. I promise you that. Yeah, and that's okay. That's okay. It's simply you don't understand the words yet. You just have to know the definition. That's how all math is. Somebody brought it up in earlier in the previous part of this stream that, you know, you're looking back at problems you're doing in Calc 1 and all of them are polynomials, and it's like, you know, how did I ever think I didn't know this? You know, like derivatives of polynomials and integrals of polynomials, you know, you think it seems a little juvenile now. The rigor is what's fun. Yeah, if it's not really tedious. Like, I mean, it's very symbol heavy. I've been through the entire argument, and I think it just serves the problem better, especially for people that don't understand every term, to just sort of show this part of the argument. The thing about complex analysis, Mr. Double Helix, is that you have to lose a lot of the graphical and visual intuitions to gain a lot more knowledge about the nature of numbers. And it's truly a beautiful, beautiful example of pure mathematics that is wonderfully self-contained and self-consistent, that just, you know, sort of demonstrates the beauty of human thought in a way, because it's truly a wonderful subject. And the fact that this is true, just by virtue of combining all three of these constants together, I mean, it's ridiculous. It's truly bonkers that that's true. Yes, they do. The unfortunate thing is you have to come up with really, really clever ways to represent complex functions, because it's a two-dimensional input and a two-dimensional output, which means you need a total of 4 dimensions to visualize it in like a Cartesian way. Yeah, and that's part of complex analysis. That's the start of complex analysis, because there's no impetus to really introduce complex numbers until you get to like group theory and complex analysis, because group theory allows you to do like extensions, you know, and then get into Galois theory and shit like that, and solving polynomial equations. And yeah, those things are more complex analysis: conformal maps, winding numbers, the residue theorem, contour integrals. Those are all complex analysis things. So yeah, we're going to get into that. And we're pretty much approaching an hour at this point. Are there any other numbers orthogonal to complex plane? Sure, you just have to define them into existence. As it turns out, you really want to stick to powers of 2 numbers of dimensions to get really good algebraic systems. You know, there's 1 dimension in the line, there's 2 dimensions in the complex plane, and then there's 4-dimensional quaternions and 8-dimensional octonions. 3 dimensions apparently doesn't really work with like an algebraic structure, multiplying them together and such. And I almost said Alexander Hamilton. I don't remember his name, but something Hamilton came up with the idea for the 4-dimensional numbers in like 1850. And they're very interesting. You should watch 3 Blue 1 Brown's visual demonstration of how to understand them as a 3D creature. But I will not be going into that today. I hope that this beautiful, beautiful integral was a satisfying continuation of my mathematical input on YouTube. And now that I've got my new laptop, one that doesn't crash just by opening up iMovie, I'll be able to finally put out videos again. It's been a little while, and I can't wait to get back into it. I can't wait to keep challenging flammable maths. And by God, I'm going to get to 1,000 subscribers before May 31st. So everybody try to help me out with that, okay? Please tell your friends. I'd really love to meet that goal of 1,000 subscribers before May 31st, because that's when I put out my first video last year. So I think I'm going to call it quits for tonight, everybody. Thank you so much for sticking around, just the 10 of you. I really appreciate it. Keep doing math. keep staying safe, keep washing your hands, keep your family close. We'll all get through this weird thing. Just remember, it just reminds us that we're all still living through the history of the human species, right? So best of luck to everybody. And good night, good afternoon, good morning, wherever you are. And I'll see you soon.